following part is a method we used in this experiment. First of all, the rocks we chose were polished sandy limestone. 5 class were chosen according to the similarity in shape and size. To calculate porosity, the 5 class were initially washed by running water to remove the originally existing salts. After oven dried at 105 degrees Celsius for 8 hours, the surface residues were swept. As we believe, tiny difference in rock physical properties may significantly affect the results. Porosity of each class sample was determined mainly through water drainage method before the start of weathering cycle. Porosity is expressed as the percentage of volume of pore space to bulk volume of sample. And the dry weight of each class was determined by subtracting the weight of crucible from the total weight of crucible and the sample class. The sample was then impregnated into distilled water until there were no air bubbles escaping from the rocks. By gently removing the excess water and the rock surface, the wet weight of each class was obtained using the same subtracting method. The volume of pore space can be calculated through the mass increase, which was only due to that inner pore space was fully occupied by water. The bulk volume of each class was measured via the volume of displacement. To simulate and compare the weathering effects of different salts, we use saturated solution of sodium chloride, sodium sulfate, magnesium sulfate, and sodium carbonate. Distilled water was used as a control. In each weathering cycle, the rock were impregnated in different solutions for 2 hours, and then oven dried at 105 degrees Celsius for 8 hours, followed by a cooling process at 5 degrees Celsius for 6 hours. The same heating cooling process was repeated for several cycles until one of the class was fully wired. The weather effect was quantified by calculating the percent mass remaining in each cycle. The residue produced in each cycle were collected from the solution after the next impregnation, which was washed and filtered to remove the salts. The dry weight of residues was determined after the same drying processes. To compare the weathering effect, we sieve the residues from the most two effective agents, and therefore we can get the particle size distribution curve. So far, we've reached the destination of method. Here comes the results.
From Table 1, we found that rock physical properties varied in all classes. The sample for sodium sulfate treatment showed the largest mass but the smallest porosity, in contrast to the rock for sodium carbonate treatment. After 9 weathering cycles, sodium carbonate was responsible for the largest mass disintegration, followed by sodium sulfate, magnesium sulfate, and sodium chloride. The weathering effect for each treatment was quantified by the percent mass remaining in each cycle. In this figure, we can see that the samples for sodium carbonate and sodium sulfate treatment suffered increase in mass loss with time, while the others showed no obvious mass decline. In the first 2 cycles, rock mass of all classes remained 100% as no residues were produced. However, from the 3rd cycle, differences in mass loss gradually occurred. We found that magnesium sulfate and sodium chloride were not powerful weathering agents, as there was still more than 90% of the mass remained. In contrast, sodium carbonate and sodium sulfate were rather effective to disintegrate rock. Rapid mass loss occurred from cycle 7, with sodium carbonate being much more powerful in weathering than sodium sulfate. From the results of sieve analysis, sodium carbonate is capable to weathering rock into finer residues than sodium sulfate when particle size falls below 0.71 mm, and these finer parts account for more than 3/4 of the total residues. From several previous studies on salt efficiency, sodium sulfate is suggested to be the most effective agent in the rock weathering process. Cook 1981 concludes 4 reasons that sodium sulfate is so damaging. First, sodium sulfate undergoes a high degree of volume change when hydrated. Second, it suffers a decrease in solubility at temperatures above and below 32.4 degrees Celsius. Third, it is very soluble, therefore a substantial quantity of solid salt is available for crystals to grow when evaporation takes place. And finally, needle-shaped nature of sodium sulfate crystals might tend to increase their destructive force due to the crystallization pressure being connected over a smaller surface area. However, the results from our experiment shows that both sodium sulfate and sodium carbonate are powerful agents, with sodium carbonate being much more effective than sodium sulfate. As Cook 1979 suggests, despite the nature of the salts involved, the properties of the rocks and the environmental conditions required to initiate salt weathering also determine the weathering effectiveness. Salts cause more damage to rocks containing a large proportion of micropores connected to macropores. Because thermodynamic assumptions that salts growing in the macropores has lower free energy of formation and tends to be supplied with solution from the micropores. Therefore, the largest porosity of the sample for sodium carbonate treatment could retain more salts in its pore space when it was impregnated into the saturated solution, thereby exerting larger pressure against pore walls during the hydration process, causing larger damage. This could also be supported by the final residues produced by sodium carbonate hydration. In contrast, due to the smallest porosity of the sample for sodium sulfate treatment, its weathering efficiency could be hidden. Among all the salts used in this experiment, sodium chloride was the least effective because certain salts are prone to efflorescence, causing little damage to stone. For example, sodium chloride tends to grow as perfect cubic crystals initially formed inside the droplet, while the large volume of materials crystallizes as hopper crystals or as efflorescence-like dendritic aggregates generally at the air solution interface. In contrast, sodium carbonate and sodium sulfate crystallize more readily inside the pore, causing extensive damage, and the crystals tend to grow within the solution as single, fast-growing, prismatic, well-developed crystals.
Due to the actual environmental complexity in desert, the results from this experiment can be more due to experimental design than the real conditions of the environment that the rock-atmosphere interface undergoes. For instance, using percent mass remaining and porosity as the indicator of rock disintegration may be not sufficient to identify morphological change and internal modification. Second, the sample size is rather small compared to those in desert, which overemphasize edge effect and fail to replicate the confining pressure experienced by large rocks. Samples have been repeatedly immersed in saturated salt solution, which may well simulate the effect of subcar or playa inundation, while it doesn't simulate any degree of fidelity the environment conditions that exist on most desert surfaces, such as pavement and typhoons. In such environment, it is probably daily cycling of the atmosphere, temperature, and humidity that is crucial in causing change in the state of salt in rock pores and cracks, which in turn promoted disintegration. Another weakness of this experiment comes from the climatic simulation by the oven, because it only gives uniform relative humidity and heat distribution around the rock samples, which fail to reflect the actual microclimate conditions in desert. For example, the temperature of rock surface can be much higher than the ambient air temperature caused by the insolation, while the inner part is cool, leading to a large temperature difference. Furthermore, the manipulation of variable cannot be achieved perfectly as a result of laboratory limitations.